Okay, so here is a question of the day. How is it going to be possible for hydrogen with only one electron to give off four different colors of visible light? So let's start with what is the universe made of? Everything in the universe is going to fall into two categories. It's going to be matter or it's going to be light. Matter is made of atoms. Atoms are made of protons and neutrons and electrons. What is light, though? Light is also called energy. That's known as electromagnetic radiation. So if you can touch it, it's matter. If you can't, it's going to be energy or light. So light travels in waves. There are three things that we can measure about a light wave. We can measure the speed, we can measure the frequency, and we can measure the wavelength. So frequency, that is the number of waves that passes through a particular point in 1 second. Usually we give that the units of waves per second. That's also known as hertz, which is abbreviated as Hz. Yes, it's named after a scientist. Wavelength, which is the Greek letter lambda, and yes, frequency is new. You can use a lowercase f, that's what we use in physics, but in chemistry it is new. It looks like a script V. Wavelength, that is going to be the distance between two consecutive waves. That is either peak to peak or trough to trough. We measure that with a unit of length, meters, millimeters, centimeters, squirrels. Well, we usually don't use squirrels. It's not standard. But any distance units we would have. And then, of course, we have speed. So that tells us the number of meters a light wave can travel in 1 second. Usually that's going to be in meters per second. So which wave is going to be faster? Do you think it's going to be the higher frequency wave or the lower frequency wave? What do you think? So if they are both light waves, they're traveling at the same speed. They're traveling at the speed of light, which is 3.00 times 10 to the 8th meters per second. This is 300 million meters in a single second. That means if we have a light wave traveling around the Earth, it can go 10 times in a single second. So how do all light waves travel at the same speed? Well, the speed of light says that if we have the wavelength times the frequency. So our speed of light is constant. It's 3.00 times 10 to the 8th meters per second. Lambda would be measured in meters. Nu, which is our frequency, that's going to be measured in hertz. So what do we know? We know that if let's go back a second. If our wavelength is large, our frequency is going to be small. We see that here. If our wavelength is short, our frequency is going to be large. We're going to have a lot more come across during that time. So let's look at our problem. So we have a microwave oven cooking a hot dog. It emits a light wave with a wavelength of 2 centimeters per wave. So that's our lambda. We want to know what is the frequency. So we take our handy dandy formula. We need to convert our wavelength into meters because our speed of light was in meters. Otherwise, we need to convert the speed of light into centimeters. So we have to convert something. So 2 centimeters per wave is going to be 2 times 10 to the negative 2 meters per wave. We are going to plug that into our equation. Meters on either side, those are going to be able to cancel. And we're going to solve for our frequency. So our frequency, when we divide out, is going to be 1.5 times 10 to the 10th waves per second, or 1.5 times 10 to the 10th hertz. So when we look at light and electromagnetic radiation, this energy, this light, is going to include visible, infrared, UV, gamma rays, X-rays, TV waves, radio waves, and all other forms of light. Our eyes are not equipped to see it all. We can only see the visible light. Everything else is invisible to us. Now, our bodies are sensitive to it. We can get sunburned, right? So if we look at other animals, so for example, pit vipers, they see the infrared color because they want to seek out the heat source. So they can see something we can't see. If we look at our regular boring white light, it is a mixture of all of the colors in our rainbow. So if we look at our spectrum, if you will, our visible light, we are going from way down over here, 380 nanometers, that's the purple, all the way up here to 780 nanometers. That's where we're getting into that red. So that tiny little piece is all the visible light. Everything else we cannot see. So if we get into large wavelengths, human-sized wavelengths, then they have very low energy. If we are going past microwaves, if we go all the way to X-rays and gamma rays, we're getting into high energy. So radio waves, really low energy. X-rays, really high energy. So the colors of visible light waves are going to depend on the wavelength or their frequency. The different kinds of visible light can be arranged into a spectrum. Roy G. Biv. Different colors of visible light have different energies. Violet light has more energy than red light. So red is at the bottom of the energy pool. Violet light, high end of the energy pool. So violet visible light has a range. Now if we start looking at black lights really close to UV light causes certain objects to fluoresce or glow. Fluorescence is where we have UV or non-visible light absorbed by electrons in the atom, and then it's emitted at slightly longer wavelengths like violet or purple, and it creates a visible light. That's what that fluorescence is. So when we look at the electromagnetic spectrum, this is an example here. Radio waves, very large scale wavelengths. Gamma rays, very short. So we've got a few different spectrums here to look at. So when we start looking at this electromagnetic spectrum, you can see that it's kind of chopped up into colors. Red, orange, yellow, green, blue, violet. There's just kind of different designations. So a lot of people, especially in the science community, get a little nerdy and they start talking about their favorite colors in terms of the wavelength of that light. So if we have small wavelengths, we get high frequency, and those high frequency have high energy. So small wavelength, high energy. Low wavelength, or large wavelength, low frequency is our lowest energy. Radio waves, AM, very low energy. So how do matter and energy relate to one another? So what we know that matter and energy have the ability to interact with one another. Matter can absorb energy. We see that when we're cooking our food. It absorbs the energy. It can also give off energy. We could burn ourselves on a hot pan. So we do have those abilities. And until really recently, most people thought that matter absorbed and released energy continuously. That's not exactly what it does. So let's think about how things are heated. So when solids are heated, they're going to emit light of all different energies. So if we look at 750 degrees Celsius, that's going to glow red. If we're at 1,000 degrees Celsius, that's going to glow blue. So if we have a warm solid, we're going to see that. At extremely high temperatures, there were some energies we didn't see at all. And some in between weren't emitted as well. So why? Well, if you see a pot being heated, it's going to gradually heat up and it's going to gradually cool down. that energy change is continuous. It's going to emit energies all the way up and all the way down. But Max Planck studied this pretty intensely. Now, Max Planck, very, very famous scientist. Okay, he was told by his professor initially to not even look at physics. Everything's been found. He won a Nobel Prize in 1918. Now, what was this Nobel Prize in? Here we go. So, his assumption was that vibrating atoms in a heated object gave rise to emitting energy. That atoms and molecules could give off or absorb energy, but only in discrete, definite amounts. And he called that quanta. But they can't do it continuously. He said that that energy was not absorbed or given off continuously, but in discrete or jumps of energy. So that is why only certain types of energy were seen. This is what we call quantum theory. Now, is that what you see around you? Well, if we think about it in terms of driving a car, it would be like saying, okay, I can go 10 miles an hour, I can jump to 20, I can jump to 30, but I can't go in between. That's not what we're seeing, right? What about a pot on your stove? Do we see this? It heats and cools gradually. So how could Planck be true? I mean, to be honest, other scientists thought he was cuckoo. They thought he was absolutely crazy for this. He nearly lost his entire scientific reputation on quantum theory. So they were like, okay, things absorb and release energy continuously. Fires, pots, pans, bodies, water. So experimentally, the quantum assumption part, super shaky. He himself tried to eliminate it from his theory. Couldn't. Albert Einstein came along and proved him right. So, Albert Einstein won his Nobel Prize for an experiment called the photoelectric effect. So, what is that? So, here we go. If we have sodium and we are trying to increase the energy by increasing the amount of red light each time. So we shine red light, blah. Do we have electrons? We shine more red light, blah. No electrons. We shine more, no. More? Okay, that didn't work, right? So we take sodium and we change the color. So we go red light. Still no. What about blue light? No. Violet light? We start getting electrons. High speed electrons. So instead of just going more of the same thing, we said, okay, let's change it up. Different colors. What are we seeing? So no electrons were emitted until the frequency of light was above a minimum frequency, at which point all of the electrons were emitted from the surface. That minimum frequency is something that is different for every single substance on the universe. But there is a minimum frequency in which it dumps all of the electrons from the surface. So, if energy was absorbed continuously, what should have happened when we gradually increase the amount of red light, we should have gradually had a few more and a few more electrons leaving. But that's not what we saw. So this told Einstein that the energy absorption was not gradual, it was not continuous, but it occurred in definite amounts or quanta. But all he did was open another can of worms. How did light move matter? Because an electron is matter. So think about it. You are matter. Have you ever had a light wave move you? That seems kind of silly, doesn't it? So what is happening is that we have this photoelectric effect. We have violet light coming in. As soon as the violet hits the sodium metal, electrons just jet off of the surface. So with the photoelectric effect, a lot of scientists were laughing at him. They thought his idea was ridiculous. It's impossible for light to move matter. So Einstein said, but light is matter. Each light wave contains tiny little particles called photons. Not protons, photons. So if we increase the amount of waves, we're just simply increasing the number of photons. But that's not increasing the energy of each wave. So if the energy of the photons is related to their frequency, that explains why higher frequency light waves, higher energy photons, can knock the electrons out of atoms. But low frequencies, so high frequency light waves, have more photons that have more energy and can move matter. So we have the photon coming in, it impacts, and the electron flies out. So the only way we can move matter is with matter. So why don't light waves move you? Well, they do. Every matter in the universe is sensitive to photons of a particular light. So think about it. What kind of light waves do damage to your atoms? Well, sunburns, UV, X-rays, gamma rays, all of those can remove electrons from your DNA. They can cause permanent damage to your cells. Visible waves don't have enough photons in order to cause that damage. So in this picture, the energy of the photon has to overcome the binding energy of the electron to the nucleus. So the nucleus has a hold on that electron. And that photon has to have enough energy to go, no, you're coming with me, and kick it out. So the energy of the photon has to exceed the binding energy in order to kick out the electron and give it off. So when we are looking at this result of Planck's work and the result of Einstein work, we get the equation where E, the energy, is equal to Planck's constant times nu, the frequency. So Planck's constant, 6.624 times 10 to the negative 34th. We've got N, well, that should be nu. So this should be a nu. It's frequency of the light wave. It's measured in hertz. So it should make sense. The energy of a light wave is going to depend on how many photons are passing through a material. Well, how many photons? That's going to be dependent on the frequency. That's how many cycles per second, right? We can line the photons up in a conga line. The higher the frequency, the more photons we can get through there. So let's look at a problem. So we have a red laser in a DVD player. The frequency of that is 4.29 times 10 to the 14th waves per second. So 4.29 times 10 to the 14 hertz. And we want to know what is the energy of this light wave. So I'm going to pull out Einstein and Planck's formula. I'm going to plug in Planck's constant and the frequency we were given. I'm going to cancel, well, try to cancel the right units. And when we multiply it out, we are going to get 2.84 times 10 to the negative 19 joules. Now that seems really small. It's 10 to the negative 19, but that is just one photon. That's just the energy of one photon. So you would think at this point, we've got Einstein in, we are done redesigning the atom, right? Beep wrong, try again. So in 1924, de Broglie proposed that because light waves act like matter, then the flip has to be true. Matter must act like light waves. So that means all types of matter, ducks, planes, trains, even you travel in waves. Now, this didn't make sense to most people. You can see that objects travel in lines, not waves. But it really does. In 1927, two scientists at Bell Laboratories proved that de Broglie was right. They took an X-ray crystallography picture of atoms and saw that the electrons actually traveled in waves. This caused yet another redesign of the model of the atom. So now we have this behavior. So if we look at the hydrogen atom, we see this resonance take place. So why can't we see this wave-like motion in normal objects? So, well, if we looked at the wavelength of a duck, it's going to be fairly small in comparison with the size of the objects. Now, electrons are already so small already that the wavelength is going to be large compared to its size. And that is going to affect the atom and its structure. So instead of circular, we're going to have a little bit of a resonance shape. And if you think about like even something as simple as a bee, if you follow the tip of the wings, we are going to get that wave motion. So what does this do? This allows us to say, okay, well, what now, de Broglie? De Broglie, of course, like all good scientists, came up with an equation. And that equation allows us to calculate the wavelength of anything with mass. Considerable mass, not light. We could calculate the wavelength of a semi. So this is another equation you are going to want on your formula sheet. So we have the wavelength is going to equal Planck's constant divided by mass of the object times its velocity. So let's look at an example. We have a bus. That bus is traveling with a speed of 28.82 meters per second. Its mass, 4,535 kilograms. I'm going to plug that into my formula with Planck's constant and say, okay, now what? Well, when we look at a joule is defined as a kilogram meter squared per second squared. So a lot of units are going to cancel out, and that's going to give us meters. Now, if you look at this, we're times 10 to the negative 39th. This is tiny.